All right, today we're digging into a super clever piece of engineering that, honestly, keeps our digital world from falling apart. It's called consistent hashing, and it's one of the biggest reasons the apps and services you use every single day don't just, collapse.
So let's start with a question you've probably thought about. You see those messages, right? Server is down for maintenance. But the whole service almost never crashes. I mean, servers go offline all the time. It's just a fact of life for these massive systems. So how in the world do they handle it without the whole thing just imploding?
Well, it all boils down to what we can call the server shuffle problem. And look, it's not just about spreading the work around evenly. The real nightmare, the thing that keeps engineers up at night, is how do you add or take away a server without causing, well, a catastrophic reshuffle of literally everything in the system. Okay, so let's check out the old way of doing things, which was honestly a recipe for disaster. A request comes in, you hash it to a number, and then you use a super simple formula, something like that number modulo 4, to pick one of your 4 servers. Easy, right? But the second you take one of those servers offline, the formula changes. Now it's modulo 3. And that tiny little change, it causes a total reshuffle. Almost every single request gets sent to a new server. It is absolute total chaos.
So, this is the exact problem that consistent hashing was invented to fix. It completely throws out that fragile, brittle math formula and replaces it with something much more elegant, something you can actually visualize, the hashing ring.
So forget about thinking of servers as a list, server 1, 2, 3, 4. Instead, I want you to picture a circle, a ring. And what we're going to do is hash both our servers and our requests and just place them as points somewhere on the edge of this ring.
And the rule for figuring out which server gets which request? It is so simple. You find the request's point on the ring, and then you just start moving clockwise. The very first server you run into, that's the one. That server handles the request. Seriously, that's the entire core of the algorithm. The source material just nails it when it says we go clockwise and find the nearest server. This server is going to be serving this request. That's it. Simple algorithm. It's such an elegant idea, and it is a total game changer.
And here's where you really see the magic. Remember the old way on the left? Adding a server meant total chaos, a complete reshuffle. But with the hashing ring, the disruption is tiny. It's minimal. The new server only takes on requests from its immediate neighbor. The rest of the system, it doesn't even know anything changed.
And it works just as beautifully when a server goes down. The requests that server was handling, they don't just get blasted randomly all over the system. Nope. They just keep moving clockwise and get picked up by the very next server on the ring. Again, minimal chaos, maximum stability. Okay, so this all sounds perfect, right? Problem solved. Well, not quite. Like any brilliant idea, the moment it hits the real world, a little flaw shows up. See, in theory, this should spread the load perfectly evenly. But in practice, there's a problem.
The thing is, hashing is random. By its very nature, it's unpredictable. And if you only have a few physical servers, say just 4 or 5 of them, the luck of the draw can be pretty bad. You can end up with all of them clustered together on one side of the ring, leaving these huge empty gaps on the other side.
And the result of that random clumping can be pretty dramatic. Let's look at server A here. Because it happens to have this giant empty space right before it on the ring, it ends up getting hit with a whopping 50% of all the requests, the whole load. That is not good. That is a terrible, terrible outcome.
So that's the next big engineering puzzle, isn't it? How do you get a nice, even distribution and balance that load without just buying a ton of expensive new servers and throwing hardware at the problem?
And the answer? Oh, it is such a clever software trick. Instead of adding more physical servers, you just add virtual ones.
This idea is called virtual nodes. And let's be super clear. This doesn't mean you're spinning up more machines, not at all. It means you use a bunch of different hash functions to give each one of your physical servers several different spots on the ring. So one real server ends up looking like it's in many places at once.
So just think back to our original problem, right? We had 4 servers, which meant we only had 4 points on the entire ring, and that's what led to that clumpy, uneven mess. But what if we give each of those 4 servers, say, 3 virtual nodes each? Boom! Suddenly we have 12 points scattered around the ring. And with more points, the distribution just naturally becomes way more dense and much more even.
And the result? It's a much, much healthier system. With these virtual nodes in place, the load becomes beautifully balanced. I mean, just look at this.
Each real server is now handling almost exactly 25% of the work. Nobody is getting overwhelmed. It's just perfect.
And you know what? This actually adds another amazing layer of stability. If a physical server fails now, all of its little virtual nodes just vanish from the ring. But the small amount of work each one was doing gets passed on to lots of different neighbors, so the impact gets spread out super thin across the whole system instead of just hammering a single poor server next door.
Okay, so this is all some really cool, nerdy computer science stuff, but why should you actually care? How does this affect you? Because this tech is, and I'm not exaggerating, the absolute backbone of the internet. It's running in the web caches that make your pages load fast. It's in the giant distributed databases that store all your stuff. It's in the massive load balancers that direct traffic for pretty much every huge application you can think of.
When it comes down to it, consistent hashing is a huge reason why the internet feels the way it does. Flexible, resilient, always on. It's what lets these massive systems grow or shrink and handle failures so gracefully that you, the user, never even have a clue that anything went wrong.
So, here's the bottom line, the most crucial point of all. We started with this terrifying, catastrophic reshuffle problem, and we solved it. Not by buying more expensive hardware, but with a truly elegant solution in software. It's just a combination of one simple idea, the ring, and one very clever trick, the virtual nodes. And that really leaves you with something to think about, doesn't it? This is a perfect example of a system designed to heal itself. So it makes you wonder, what other amazing ways can we design complex systems to not just handle failure, but to expect it and adapt to it, all on their own?